Okay, so in this video I'm going to talk about the concept of trusses, and I'm going to approach this from just totally first principles. This is assuming that you don't know anything about engineering at all. So the first thing, I'm going to be going quickly, but I'm going to assume first principles. So the first thing we're going to need to know about is we're going to need to know about forces. Okay, so a force can be defined as a push, a pull, or a twist. Forces in Australia and most of the world, they're measured in newtons. So it's written with a capital N or 1 newton, written like that. Okay, so a push, a pull, or twist, but then we have to define what is exactly 1 newton. Well, what 1 newton is 1 newton is the force of an object of 1 kilogram mass accelerating at 1 meter per second. So instead of 1 kilometer per hour, 1 meter per second is about 3.6 kilometers per hour. And then it's increasing its speed by that rate. It's going every second, it's increasing its speed by 3.6 kilometers an hour, or 1 meter per second every second, which we can write like that: 1 meter per second, or 1 meter per second squared is how we tend to write it. Now on Earth, things, when we drop something, I just dropped a pen lid, when things fall on Earth, it falls at 9.8 meters per second squared. But in engineering, in the high school subject engineering studies, we're allowed to use the value of 10 meters per second squared. In practical working environment, you'd always use that because you don't want to give up 2%. 2% is a lot of money. But just to make our calculations easier while we're still learning, we're allowed to use 10. So the idea is if I have an object that's 1 kilogram on Earth, if it's just sitting on a chair, the force that it exerts on the chair is going to be 10 newtons on Earth. It would be less, it'd be like 1.6 on the moon, right? So that's the number of newtons. That's covering a lot of content that we do at the start of the course. But that's what we really need to establish to start off with. A force is a push, a pull, or twist, a bend. In Australia and most of the world, in Europe and pretty much everywhere scientifically, like NASA for instance, they measure forces in newtons, which is written as a capital N because it's named after a person, or the unit is written as 1 newton, lowercase. 1 newton is defined as 1 kilogram times an acceleration. So you might be familiar with F equals ma, so force is equal to mass times acceleration, and the mass, we always measure our masses in kilograms, and our accelerations in meters per second squared. It's interesting to note that 1 kilogram is 10 newtons, not 10 kilonewtons. That's a very different thing. Okay, so that's where we're starting. We're starting with the concept of forces. And then after we have some forces, we're then going to talk about, well, what is the structure that we're most interested in? Well, it's a very simple structure to understand, to say a column that's being squashed. So if I have a column, or actually, we'll stick with a column for the moment. If I have a column that's being squashed, if I want to know whether or not it's going to break, what I need to know is I need to know the force divided by the area. So that formula, stress equals force over area. If the force is too great, the easiest thing to do as an engineer is so what I do is I compare the force, or the stress bit that's being applied. This is stress is force over area. I compare this stress to the strength of the object. Now I like to use as an example steel. The steel is over 300 megapascals. Steel's pretty strong. It's a high value, right? Concrete could be 20 to 40. But if the stress that's being applied by the loads on this column is too high, well, we have two choices. One is that we could use a high quality steel. We tend not to do that. What we're more likely to do is we're likely to increase the size of the column, or we're likely to redistribute the loads. So we could add in more columns, for example, might be a way of approaching that. Okay, so once we've established why we do these things, well, that's one thing we look at. This force In a column, the force is acting through the center or the axis of the column. And that is relatively speaking in engineering, that's a simpler example. As you learn later down the road, columns actually become the more complicated example. But for the moment, in this simple example, where the load is being applied directly to the center of the object, that's a fairly simple example. Now, the same thing applies if we have a rope that's being pulled. If we have a tug of war and we're worried that the forces on that rope are too high, there's too much tension on the rope, what we could do is we could probably use a bigger rope in that case. Or we could change the material and we could use something that was a tougher reinforced rope. Okay, the next thing we're going to talk about is we're going to talk about when we have to span distances. So if I'm building a house, well, one way of building a house is to have the roof being supported on rafters, right? Pieces of wooden or timber members that support the roof. On top of that we put battens, and then from the battens we put other things. What happens there is the weight of the roof is being supported on this member, and in this case we would say that it's behaving, that's showing the deflected shape. That beam, or that rafter, is going to be bent. And bending is a much more complicated, relatively speaking. I'm just going to turn that side view. Right, what we're going to do is we're going to look at that same rafter. Well, we wouldn't really normally have flat rafters. What we're going to have a look, in the case of a rafter, it would look probably like that. And then it's going to bend a little bit. Yep. It's going to deflect. What I'm going to talk about instead is we'd imagine that so the same is true for some floors, maybe if it's second story floor or all the houses that have timber floors. Most of the stuff I did worked with timber floors. They would have bearers and joists. And again, yesterday I was watching an off-the-grid video about some guy building a cabin in the woods, and he was using pretty big timber bearers to hold up the cabin. So in this case here, we're spanning. The load of this house is going to be applied. In this case, we're going to simplify it just to one single load on the middle of that beam. Now in that case, this thing is going to deflect. And deflection is complicated. It's complicated. So the first thing is, what we want to do first is we want to see whether or not these reactions, whether or not these supports will be strong enough. It's possible that we need more supports. One of the things the off-the-grid video is talking about is that they put an additional support in, they put a footing for an additional support if they decided they were going to need it later. And we could say, well, how could we design beforehand to see whether or not we need additional supports? So what we need to do is we need to find out how this load is going to be spread from this side and this side. And that's the first thing we need to look at. The next thing we have is, it's pretty intuitive that if you took something like a metal ruler and you put some load on it, what you would notice is that the longer the ruler, if you had a 30 centimeter ruler, a 300 millimeter ruler, versus a meter ruler, you're going to have much, much more deflection on the bigger one. Right? Does that make sense? Intuitively that makes sense. You might think of other examples. Some of you who may have worked with timber might have seen that it's much easier to make a long piece of timber bend when you stand on it than it is to make a short piece of timber stand when you bend it. So that's a factor that we need to consider. Now, because bending is complicated, now my plan is to do, the next video I do today will be on talking about bending, coming back to that. What someone figured out was that if you want to build a long bridge, if you don't want to worry about bending, what you can do instead is you can build a truss. That was not a great truss. There we go, that'll do. Okay, so what this truss does, I'm going to simplify it a little bit first. Okay, when I drew that ruler a second ago, I drew the ruler looking like it was flat, right? I don't know if you guys are familiar that if you take a metal ruler, and it would be a great idea for me to actually have a metal ruler for this video, but you guys, we can get access to a metal ruler later. If you want to bend the metal ruler, is it easier to bend the ruler when it's flat or when it's standing?
Flat.
It's easier to bend when it's flat. If you take the ruler and make it stand up, it's much harder to bend. And even though the area is the same, in the case of bending, in the case of beams, it's actually much more useful to have what we call, if we have a shape, in engineering we use the term breadth and depth. And what we find is that big D is good. We want to have a big depth, right? The bigger the depth, the stronger the material. So if I could buy two pieces of material, I could buy a 100 by 100 millimeter, what in America would be known as a 4x4, or I could buy instead a 50 times 200. Which is the better one to buy?
The long one?
This one here. Okay, so this one here is better for a beam. But if you're using a column, well, you probably want the squarer one, because the squarer one we want it to be strong in both directions. Yeah? But they both have the same area. They both have the same area, but the difference is that this one has the big depth, and having big depth is going to have more strength. What's interesting is that, well, so there's a video done by an Irish YouTuber who talks about I-beams. I'll maybe some other point talk about I-beams. But I-beams are a common engineering shape. And they used to be called RSJs if you go back sort of 40 or 50 years ago. RSJs, or I-beams, or universal columns, universal beams is another term. You might call them UB or a UC. A UC is going to be square, and this would be more like a UC. For universal column, a universal beam is usually taller. I remember when I first was learning about beams, that someone talked about how you could take a beam, one of those I-beams or whatever, and what you could do is you could cut out of that beam, you could cut this shape, and then you could slide it along until you then got a new shape. You now got this shape, with those hexagons being empty. And the idea is that the inside, the part that matters when things are bending, is this shape, is the distance from the center. Right? The further away you are from the center, that's where it's more important. For my year 11s, they should be familiar with this, the idea that the maximum tension, the maximum compression are both on the edges, and in the middle there's this area called the neutral axis. It's not really doing a whole lot of work. So we could just cut that area out. If we're smarter, if we don't want to cut along these edges, if we just want to like plasma cut or water jet cut the whole thing, what we could do is we could say we actually know that in the middle of the beam we have even less, and we can make the circles get smaller. And that's another way of designing our beam to be efficient, because we know this part here isn't doing a lot of work, but it's costing us money and it's adding weight. What we can do is we can cut out that steel that's not doing as much work and just let the rest of it do the work, right? But if we expand that to the extreme version, rather than just having a really deep beam, what we can do is we can actually get rid of the bending forces at all, and we can just turn it into a horizontal column. Right? What we're doing here is that we're getting rid of all of the bending, because bending is difficult. Instead, what we can do is we can just turn everything here into squashing or squeezing forces, and that's what a truss is. A truss is a way of using the same amount of material, but instead of having bending, which is bad, we can turn everything into compression or tension, into squashing or stretching. And we can put all of those forces into squashing or stretching and put them onto this shape. So by doing that, we don't need to worry about bending. Bending is much harder to design for. Bending is also, it generally requires more material. So trusses can be a very good solution. We drove over a truss bridge to get here. We went over Tom Ugley's Bridge, which is in Sylvania in southern Sydney. Trusses were really popular. We're going to say that they were popular during World War II and immediately after World War II. They've since gone out of favour, mostly due to the widespread use of concrete, I would say is probably the biggest factor. Anyway, so what we're going to look at now is we're going to learn how to find what the forces are in the different parts of this truss. And the reason we're going to do that, the reason why we want to do that, is because we need to be able to find the forces in the truss so that we know that they can be big enough. Because if we know the forces, we can find the stresses. We said earlier that stresses is force over area. So if we can find the forces in this truss, we can then find the stresses, and then we can compare the stress to the strength. We said, what was the example we said for steel? What did we say was a reasonable strength?
More than 300.
More than 300. So the idea is if we can keep these stresses under 300 megapascals, then we can say this truss is fit for purpose. It's not going to break. Now that's not quite as simple. We'd say we'd probably half that number because of what we call a factor of safety. There's a whole bunch of other factors that go into this. I haven't even really talked about how we calculate stresses all that much. I just threw in there a second ago that the unit for strength and stress is both measured in megapascals. But the idea is at the moment we don't even care about the stresses. All we want to do is find the forces. The forces is the point of this exercise. Now the very first thing we need to do before we can do anything else is we need to be able to find the reactions. And how we draw that is usually something like this. So to start off with, if I have 100 newtons, now 100 newtons is equivalent to a 10 kilo bag of rice sitting on the middle of a beam. What would you predict would be the amount, let's say I had it sitting on 2 chairs, right, or 2 stools, right? Three-legged stool. What do you think the load would be on each stool?
50.
50 newtons, yeah? 5 kilograms is going onto each stool, right? Now imagine my stools are made out of paper instead of out of timber. 5 kilograms might be enough to cause a paper stool to fall down. My origami stool might fall down. But even for timber, there is a certain weight, right? 500 kilograms, right, or 5,000 newtons, might be enough to break a timber stool. Maybe something under a lot less than that. I have seen stools break with people who weigh less than 500 kilos sitting on them. Okay, so what we wanted, you correctly identified that in this case here, the reaction, right, for every force there's an equal and opposite reaction. If this 100 newtons is going to stay where it is, if it's going to not be broken, it means that if we have 100 down, we have to have 100 also going up, right? And so how that works is we have this rule. I'm going to write the rules I'm going to write the rules over here actually. So our first rule is sum of the forces in the y direction have to equal 0. And in this case, I'm setting my y direction as vertically up. So that means if I have 100 up, I have to have 100 down. Right? That makes sense. Okay, a little bit more complicated is what if I said instead I had 100 and I had a small amount, let's say 20 newtons going to the left. What's going to have to happen? If nothing is pushing back against that, what will happen?
It'll break.
Yeah, so let's say if I have my bag of rice and then someone taps the bag of rice, if the stools can't resist that force, everything's going to fall over and collapse. So one of these 2 stools has to push back. Now, a little thing that when we're talking about, say, structures, when we're talking about bridges, for example, everything that we work with, one side is on a roller, right? You'll have to imagine, it's funny to think of a bridge, one side of the bridge being on rollers, but they are. You can actually go down and look at them. You can see the rollers on the Harbour Bridge, for instance. One side is pinned and one side is on roller skates. Right, so I like to give them names. The one that's pinned I like to call Penny, and Penny is the more complicated one. Right, so I have Ricky the roller. Ricky the roller, she can only take reactions in one direction, whereas Penny the pin, she can take the horizontal reaction. Okay, so we've got that concept, but that means that see how this 20 newtons and this 20 newtons, they cancel each other out? So we now have our next rule, which is sum of the forces horizontally, or in this case, we should actually, more accurately, we should say the x direction. But we usually set the x direction as horizontal. They also must be 0. Just to check that we're familiar, what this symbol here is the Greek letter sigma. It's a capital sigma, which means sum of. The sum of all the forces. So that's what we're saying there. Okay, so that makes some good sense. We've got that going for us. The next thing we need to worry about is, okay, well what if Well, I'll do an easier one. In this case here, I've now got 2 bags of rice, right? And they're each 10 kilograms or 100 newtons. What are my reactions going to be here?
100 newtons.
Yeah, that makes sense. Because where we have a symmetrical loading, it makes sense. It makes sense that the loading is going to be symmetrical. Okay, what about if I get rid of this one now? Now it's getting more complicated. What do you think this is?
75.
Oh, okay, well we've got a prediction. Okay, so I'm going to give you some distances. I'm going to say, for the sake of this, I'm going to call this 1 metre and this 2 metres. So, what do you think this one's going to take?
30 or 33.
33? Okay, but imagine you are both carrying 66. Yeah, okay. If you're the one if you're carrying a fridge, for instance, right, something like that. Imagine you're carrying something, right, and you're carrying it with your sister, and your sister, she's on one side, and you can see, you just know that you're carrying, the load is closer to your side. Well, what that means is probably that you're going to be taking, in this case, 67 versus 33. Now, that's pretty intuitive, right? What if I then put back this 100 newtons in the middle? So if I tell you that it's like that, what about now?
40, 60?
Well, our prediction would be that this one here would get 50, and this one here would get 50. That's a pretty reasonable prediction, right? Okay, so what we're going to do is, the problem is we have 2 unknowns, right? We've got a prediction. We can write our prediction up over here. This is going to be something that ends in a 7. I'm just going to write my prediction up here. Something ends in a 7. This is going to be 117. And this one here is going to end in a 3, so it's going to be 83. Just checking that those numbers do in fact add up to 200. Sounds right? Okay. What we're going to do instead is we're going to give these names. Now there's this board game called Ra. And every time you play the Ra tile, it says in the rules you have to yell Ra. So whenever I write RA, I like to say it as Ra. Also, I find that it does occasionally keep people's attention and that they wake up. On the other hand, I have RB, which I always like to say stands for red balloons, right? I don't know, just a punsism. Okay, so what we've got here, we're going to try and find RA and RB. Now, what we know is that because we know sum of the forces vertically equals 0, we know that 0 equals RA. I made that positive because see how this is going up? I predicted that it's going to go up. Minus 100 plus RB. The problem is I have 2 unknowns. I can't solve a problem with 2 unknowns. Well, I can if I use simultaneous equations. But at the moment, I don't have enough. If I look at my other side, I have no horizontal forces. So I need another equation to make this thing work out. So in steps this concept called moments. Now, if I was doing this in normal classes, I'm always pretty excited because talking about moments, well, let's just say it's a big moment. I have a couple of songs we play and we talk about how this is the most important part of the course. I can get rid of that now. And the formula we're going to use is this one here, where I'm going to say the sum of the moments equals 0. Now, what is a moment? Well, it's a good question. A moment in engineering is a turning force. We have regular force, we said a push, a pull, a twist, right? In the case of a moment is the turning effect. Now, most people, when I normally have covered this, I'd normally start with levers, right? So we're going to take a quick step away for a second. If I have a lever, and I have 1 meter away and 2 meters away. So in this case here, if I have someone who weighs, let's say 40 kilos, which is 400 newtons on this side, what would I need to balance that lever?
800.
No, do you think you need more? So Archimedes said, give me a lever long enough and a place to put it and I could lift the world, right? So if you have, when you think about the Milo spoon, right, the Milo spoon, that's your fulcrum, the lid of the tin, right? Do you need a big force or a small force? If you've got the long lever, you're going to need a bigger force or a smaller force.
Bigger.
So you can't physically, with your finger, you don't have enough strength in your finger to lift the Milo tin, do you?
No.
So what you need to use is you need to use a spoon, and that spoon increases the force that you can apply. Now, it doesn't save you energy, right? It doesn't save you energy. You still have to do the same, use the same amount of energy, but this tool allows you to spread your energy out over a longer period of time, or distance, more in fact. It allows you to spread your energy, do your energy over a longer distance, but what it does is gives you an increase in force. So we can see here, if I've got a fat kid, right, a friend of mine, he used to have a shirt that said, "Fat kids always win at a seesaw." If I've got a fat kid, well, how do you beat the fat kid at seesaw? Well, you shift the seesaw so that you have a longer seesaw, and that way the smaller kid can still balance. The kid who only weighs 20 kilos can now balance with the fatter kid. Does that make sense?
Mm-hmm.
So that concept we call moments. And the rule for moments is moment equals force times perpendicular distance. Now it's important that we always remember perpendicular distance. We'll cover that later, right? We'll get to that when we come up to an example. But for the moment, what we can see here is the moment on this side is 400 times 1 meter, right? Now, assuming that this is going down because of gravity, we have a anti-clockwise force of 400 Newton meters. And on this side, we have another force of 400 Newton meters. This one though is going clockwise and this one's going anti-clockwise. And you can see that those two forces are now balanced. Right, we have 400 and 400 Newton meters. So they're now balanced. Okay. So what we can do here is when we start getting to really complicated load situations, what we can do is we can use this formula, we can use this moment formula to solve our problems. Now, why this is really interesting is, I'll get to it in a second. Okay, so I wrote sum of the moments. Now, when we measure our moments, we can measure our moments anywhere, right? In the case of our lever, we measured from the middle, right? We measured from the fulcrum, right? But here we don't really have a clear fulcrum. So we could measure from here, or here, or here. We could measure from anywhere. But what I've chosen to do is I've labelled already these points. I'm going to call this point here A, and this point here B. And it doesn't matter where I measure my moments from. I'm going to later prove that it won't matter even if we go from C or D. But what will happen is that they're going to be balanced. Okay, but for the moment, what I'm going to do is I'm going to start with A. So moments for about A equals 0. What that means is I've just said the sum, that means adding them all up, all the moments about A measured from the point A are going to equal 0. Now I'm just going to say it as a reminder, M equals force times D. Force times D. And then I'm going to write underneath that just perp, just to remind myself that's perpendicular distance. Okay. So let's have a look at the forces. Well, I wrote 0 because I know that's the final answer I'm going to get to. And I've said here, well, my first force is 100 newtons. How far away is 100 newtons from point A?
1 meter.
1 meter. So, okay, I wrote 100 brackets 1. We're happy with that? Yeah, okay, cool. Now, I also want to establish a convention of clockwise or anti-clockwise. Now, when I was at high school, and even when I was at uni, I often used anti-clockwise as positive. Once I became a high school teacher, I just said, I am just going to use positive every single time. So you might see HSC answers where they've used anti-clockwise as positive. Me, I have just decided for consistency, I'm always going to use clockwise. Okay, so what I have here is 100 times 1. Now, what I'm going to do is I'm going to put my finger on A as though it's the center of a wheel, and I'm going to spin like I've got a chocolate wheel. You've seen those, right? Where I go, which way was that going? Is it going clockwise or anti-clockwise?
Clockwise?
Clockwise. Okay, great. Now, I'm happy with that, so that should be positive. But I've now just remembered, I've left out one of the forces. Now, you won't see this written very much in textbooks. I don't know why, I just don't write in textbooks. But there was a force here, RA. Why wouldn't I have written down RA? What's the distance of this force? The reason it's R is for reaction. Yeah, it's to say that it's a force that's reacting to everything else. It's not a fixed force. It's a force that's going to change depending on the load that's being applied to it, right? Why didn't I write down RA? Well, what's its distance? The distance of this force from point A, what is that distance? 0. Okay, well, when I multiply RA times 0, what happens?
0.
It just becomes 0. So we can ignore it. And I write that in blue to say I have ignored this. Yeah. Okay, then I have plus 100 times 1. Why did we say it was plus?
Positive?
Because it was which direction?
Clockwise?
And we've said we're going to use clockwise as positive. Okay. The next force is, again, 100. If I was smarter, I would have made that different, but okay. What is the distance?
1.5.
1.5. Okay, so I've got 1 plus 0.5, which is 1.5. Okay, the next force, what's the next force in our diagram? We've got 4 forces. 1, 2, 3, 4. What is it?
The other reaction?
Yeah, RB. Okay, now I always write minus RB, or I might write minus for my forces until I've proven that they're clockwise or anti-clockwise. The reason for that is a minus turns into a positive way easier than the other way around. Okay, and what is its distance away? 1 plus 0.5 plus 1.5, which equals 4 meters. Is that right? 3 meters. Okay. Okay, so in this case, let's have a look at RB. If I put my finger on A, because it's the center of my chocolate wheel, and I push up in the direction of RB, which way am I going to do? Da-da, 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 da-da. Which way is it going?
Anti-clockwise.
Anti-clockwise, so it stays negative. In our example, it's going to stay as negative. Okay, so now that we've got that, what we're going to write here is we're going to write 0 equals 100 plus 150 minus 3RB. Okay, now I don't like to do this, but the first couple of times I always write up, if I'm going to add 3RB to this side plus 3RB to this side, they cancel out, yeah? And what I end up getting is 3RB equals 250. Now if I went to the shops and I bought 3 red balloons, but they must be really, really big balloons, and they cost me $250, how much would you guess each balloon cost? It doesn't need to be perfect, just a rough figure.
80.
About 80 sounds about right. Right, so what I'm going to do then is I'm going to say, well, RB equals 250 divided by 3 equals okay, now I've written up here, but the only reason I can write up is because here I made an assumption. What was the assumption I made about RB?
That was negative.
Why did I assume it was negative though?
Because it's going anti-clockwise.
How did I know it was going anti-clockwise?
Because you did the thing and then you went like that.
Yeah, but I had to assume that this arrow was indeed going up. I don't know that it's going up. I mean, in this case it makes sense, of course it has to go up. But there are situations, right, where I could have a beam sticking out over the edge, right, where I might have to hold down. The reaction actually is, instead of it pushing up, might actually be holding down. Imagine if you had something like a surfboard stuck between 2 bricks. If someone stood on the other side of the surfboard, the whole thing would lift off, yeah? In which case you'd need to have to tie it down to those bricks in order to stop it from wobbling, yeah? So in this case, I assumed positive. So I'm going to write here, assume up, therefore anti-clockwise. Now here, my answer came out as being positive, right? So I can write here positive, therefore my assumption was okay, therefore it's up. That's how I figured out which way my directions was going. Now this question, okay, so I'm just going to let that breathe for a second. That's only helped me to find one reaction, right? Let somebody help me. Oh, damn! I rubbed out my predictions.
83, 177.
83 and 177. Okay, well that looks pretty good, right?
Mm-hmm.
Now, that's only given me one side. I can now write in here 83.3. Well, then what we have to do to find this one, we could do the whole thing again. And we might do that again. But most of the time what we would do is we'd then go from here and we'd say sum of the forces vertically equals 0. Now I could do the equation for this particular run through. I'm going to try and keep things quick. And I'm going to say, well, okay, I know I have 100 down. I'm just going to draw a little diagram. And I find that the easiest way to go. 100 down. And how much up do I have?
83.
I have 83.3. So how much is missing?
17.
Ra equals 166.3. Yeah? So that is a totally acceptable way of solving this. Is we can just say, well, we've used the other equation. If you haven't done simultaneous equations, you're not comfortable with simultaneous equations, I won't go into the detail of that. But effectively here what we're doing is we're using the second equation to find our other unknown. Now, in this particular case, I am going to prove that we could take moments from another location and still get the same answer. Right? So what I'm going to do here is I'm now going to clear this off the board. I'm going to look at it again. I'm going to say, now I'm going to measure instead moments about B. Okay, if I'm measuring from B, my first force is RA, right? Ra. How far away is Ra? 3 meters. Okay, now, is it going clockwise or anti-clockwise? So I've written minus there, but in the meantime I'm going to go da 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 da. Which way is it going? Clockwise or anti-clockwise?
Anti-clockwise.
It's going regular clockwise.
That's regular clockwise, right? So we're now going to turn that into a plus. Yeah? We're going to turn that into a plus. The next one is 100, and how far away is it? It's 2 meters away. Okay, again. Da 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 da. Which way is it going? Anti-clockwise, so it's going to stay minus. We've got 100, and how far away is it? It's 1.5. Make that a little bit curvier. Okay. Da 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 da. Again, minus. Yeah, we're happy with that? Okay, and then we have, of course, I'm going to write this one in blue because everything I write in blue you can ignore. You don't have to write down if you don't want to. You probably won't see it written in a textbook. Okay, now what